Good afternoon, everyone. I think everything I wanted to say has already been said about Michael, but I just want to say a couple of things because I had the pleasure of serving with him when we were in TAC. That was the highlight of my self-knowing Michael. I got to know him a long time ago. Just to let you know, when I started as assistant professor, my training was in bridge engineering and structural health monitoring. While I was a student, I helped other colleagues in the SHARP project. They were doing a lot of fiber with Professor Naaman in Michigan, but I didn't really do anything in my research on material. So I was a structural engineer, and when I became an assistant professor, I immediately realized I'm not going to be able to get tenure if I rely on my structural health monitoring and bridge engineering, because every project takes 3-4 years to get the results, and to publish at that time was about at least 2 years. So I realized I need to do something else. And that something else became when I saw Chelik and Michael present their work at ACI about high-performance concrete. Professor Wires from Virginia Tech and even Michael's thesis at the time was a very useful product. So I realized I need to do something in materials, and I started talking to our DOT. It is in the early 90s, and they realized that, yeah, we could do that. High performance, what's that? And nobody knew what it was. So I started focusing on that, and I think VTRC, and I have to admit, everything I needed was there. So I cheated, and I looked at your reports, and I was able to kind of put my proposals together. And to my surprise, I was selected by the DOT to do the work. And I ended up, to do the real work, I needed to talk to many of them, and Michael and Chelik were a good resource for that. And I remember you coming to New Jersey, doing a lot of training for the New Jersey ACI chapter, and I was sitting in the back, absorbing everything they're saying on cracking. So so with Michael, it turned out that he's the only person from a DOT where I can meet with him 5 times a year, 2 times at ACI, 1 time at TRB. Sometimes TRB had some conferences where he was there, and with TAC on the summer meeting. And those were, times where I would have very intimate discussion with Michael. Him and I were in the same background, and he would bring subject that, to my surprise, he acted like he didn't know in the beginning when he puts the question out. And I was like, blah, 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 telling him what I know. And he says, yeah, but I wrote that report. I did this, I did that. So he was really very knowledgeable. One incident that took place, our DOT wanted to use, they put a moratorium in using overlays. They said, well, if we're using high-performance concrete, why do you want to do overlays? Forget it. We're not doing LMC, we're not doing anything. Until a project I was involved with from a distance, they had a lot of cracks. It was HPC project, but I think the designer or the contractor, it was settled, we don't know, but the camber didn't come out right. So when they were doing saw cutting, it was the steel. They were cutting the steel in the top of so they needed an overlay. And then came, what do we use? And I read the LMC report that Michael did. I said, LMC. They said, oh, no. We had bad experience with that. And it turned out the curing period. So they were specifying 7 days of curing, and which is bad because you need the latex to coalesce. And I read that in Michael's report, and I acted like I know what I'm talking about. And I said, you can't cure for 7 days. Why? I said, VTRC did it, and they have a reduced number of, because you need, they said, no, but the cement the concrete need to cure, so you need the strength. It turned out, I did some work in the lab. You need to have an optimum point. It turned out it's not 1 day like the contractor wants to do. It about 2 to 3 days was the optimum point where you can get the strength, but you can get also the elasticity that the polymer can give you, which I think. So for that, I think I owe, I don't want to say my whole career, but I owe my starting point to Chelik and Michael, both of them. And Michael more because I felt like I learned from him. Although I act like I'm a professor and I teach the student, but with Michael, I felt like I'm the student and I'm learning and I'm listening. And his area was cracking, monitoring, and concrete material. And I think I emulated that model in all my research until now. I always, whenever there's a crack or some problems with the bridges, I talk to the DOT and say, let me look at the material side of it. Let me look at the loading side of it, and let me monitor what's going on. So those are, this is a tripod that helped me a lot in my research. And this one, I think, we wanted to know, like, sometimes we had, this was a fiber reinforced SCC. We tried to promote that with our turnpike. We had an on-call agreement with them, and they gave us a project to do. But we didn't really, in the setup, in all the literature, nobody can measure what is the concrete strain, especially in the restrained shrinkage test. You only have indirect relationship. You measure the strain in the steel, but you were never able to measure, what the concrete strain is. And that's what we want. That's what we're after. So I thought, okay, what if, what we do, and I talked to Mike about it when we were in TAC. We had hours and hours, if you know, I think Michael knows what TAC. We used to meet Friday until like Sunday, and we sit, 10 hours a day talking about things. And when Michael, we discuss a lot of things, but when Michael speaks, everybody said, okay, that's it. We move on, because he always said the right things because of his deep knowledge. So I really feel like, I always, when I sit in a group meeting in discussion, I feel like Mike is here because his concrete experience and his, touched everybody, including on TAC. And that's why he led the repair on TAC, and he did a great job with that one. So I really feel he is greatly missed, in our community. So let me get quickly, I know you guys need to get to lunch somehow, but so our project, this one, was about, let's validate, and Professor Weiss, Jason Weiss, did a very nice equation from the monitoring the strain in the steel ring, you can detect, or predict what the concrete strain is. So we tried to see, is that correct, and how much would that be? So I'm going to go over that validation process by looking at the experimental program and how did we modify the testing setup to be able to pick up the concrete strain. So I'm going to go over the experimental program and then the results, and then at the end, some conclusion. So as you know, with SCC, it's very high cementitious, and one of the issues in the early stage was shrinkage, because of its high cementitious. So we proposed adding fibers. And this was part of our work when we worked with the RECAST. RECAST was a center, the only federally supported center at Missouri with Professor Kamal Khayyat. So we got some funding from that center to be able to do the work, but also Turnpike, partly funded this work. So we needed to basically reduce the shrinkage, but improve the consolidation in terms of fiber. So we tried to look at the mixed design. We used mainly polypropylene fibers because the agency was not really too excited about steel. They always say, oh, we get pitting corrosion in the steel in the negative moment region. We don't want the bridge deck to look brownish all the time. So, but we ended up doing the polypropylene fiber. We tried 3 different mixes with different volume fraction. And we mixed it in the lab, and so I tried to look at the modified setup for the ring test. So instead of just putting the steel, the foil strain gauges on the steel, we tried to also measure the what we call the hoop stresses or the strain in the concrete ring. To be able to do that, I don't know if you could, here, okay. So you probably could see it here. I think I have another picture, but this is the restrained ring. We had the waxing of the top, so the shrinkage is only in one direction. And then we added what we call, with the help of the student, we made a template to make vibrating wire strain gauges almost like a closed loop. So this way, no matter how the concrete shrinks, these vibrating wire would always give you the, and this is the picture here. So this is the template. So when we cast the ring, we are able to put this template. These are vibrating wires, 6 of them They're connected together. They can move this way. And Geocon helped us, and now I think they sell this gauge with the legs welded to the gauge. So in other words, the gauge length is slightly modified, and then all what we do is we insert. We put this template during when it's being mixed in French concrete, and then we have kind of bolts coming out, very thin bolts. They don't interfere in the shrinkage behavior. Sometimes they do if they are too deep. So we try to keep them with the template at a certain height, and then what we get is that when the concrete is shrinking, the ring is shrinking. These vibrating wires, some of them will be in tension, some of them will be in compression. And you'll end up measuring over time what's the strain in the concrete at different locations. And we also look at the strain gauges on the steel and the inner side of the steel ring. And what happened, I'll show you a curve. From the vibrating wire, you can see the strain is going, and we test cylinders at 1, 3 days, 7 days, 14 days. So we are monitoring what's the cracking capacity of that concrete. So we have that line, and we also know from the vibrating wire what is the strain in the concrete, and then the minute that line from the capacity hits that line, it means you expect a crack to happen at this age. And usually the students are very good in saying in 2 or 3 days we're going to get a crack at this location. And then they go with this digital small microscope, and they scan the ring for the cracking, and they are able to measure the crack width and the crack length. So because that's how we measure what is the cracking in density and so forth. So this was a kind of modification of the AASHTO T334, I think, and it was provisional when we started that. Now it's permanent. The ASCE has also, I think, Jason was able in getting the ASTM standard, but the ring is a little bit smaller than this one, so we still use AASHTO because that's what fit the bridge decks. So if we look at the different mixes, here is the ratio, of the compressive strength. We did all the testing on it, and you can see that the fibers has a slight influence, on the properties. However, you can see that the strain, the more you go with the fibers, there's an enhancement in the cracking strain. And this is the change in length. So basically, we measure from the specimen the ASTM C157 just to see what is the free shrinkage properties. Why is that? Because you cannot spec the ring test for field measurement. That's impossible to be able. We realize that. So what we did is we tried to put a limit on the free shrinkage that correlates very well with the ring test. So in other words, whenever the ring test was showing that it will crack, we monitor also the free shrinkage strain, and then that would be the limit that we have to specify. We ended up in the specification, this was around 400, meaning. So this test is useful, but for cracking, it doesn't give you the indication for the potential of cracking. So we had to apply the limit that we correlated with the other one. And you can see here, this is the strain at 28 days, basically. So here is so you could see 3 lines up going in tension and compression, and 3 lines going in tension. So in this case, what will happen, and this is the cracking strain here. So in other words, the crack will happen here, okay? And we try to confirm that with the strain gauges with falsing. I'm going to go a little bit quick. This is some of the cracking pattern, the map of the cracks, where does it occur. We also look at it, for each ring we had, for each mix we had 2 rings. So we monitor the fold strain gauges at the same. So each vibrating wire, now we have 6 fold gauges instead of 4. At that time we did 4. So this is another ring. You could see that the cracking, and we can get the cracking age, okay, and then the cracking width. And so I'm going to go through this quickly. Same behavior on most of them. So actually, the shrinkage is not uniform. We assume the shrinkage is uniform and radial. It's not. Most of the time, it depends on where the drying is happening in one location more than the other. But more or less, if this is symmetric, more or less would be. So these are all the mixes. I'm going to go through them quickly. So you could see here, this is the cracking days. That the number of days increases, the potential for cracking decreases when you increase the fiber percentages that's expected. And we have also the number of days from the foil strain gauges and from the vibrating, and they kind of coincide also. We looked at what Dr. Weiss did with his student. Basically, from compatibility of the strain, they were able to derive this equation. So we said, let's see how that works for fibers, for the ones we have. And we found out that it's really very good, in terms now, when you add the fibers, you start missing it a little bit. The equation does miss that a little bit, but not with not much difference. And so we corrected that equation, and we added a correction factor that will allow you to basically, if you have fibers, to be able to predict when would it crack and what would be the cracking strain. So now we did a couple of probably 11 bridge decks with fibers. Turnpike has a standard mix. We made it not SCC but FR-HPC, so the HPC mix, but with only 5 to 7 pounds of fiber added to them. We made it very, very simple. It can be pumped, it can be pulled from a chute, and we have a specification that's working. We are doing a demo now with the New Jersey DOT to start using that as their standard mix. And we did the crack mapping for 3 years before the bridge opened to traffic. After the bridge was open to traffic, they allowed us to go there and do the same crack mapping, and we saw about 33% reduction in the number of cracks and in the crack density, that is, especially in the negative moment region. So I think for the vibrating wire, it's a little bit of work, but it's really very informative to get the strain in the concrete. So you're not really trying to use the equation that might not give you all the boundary conditions. But still, as a reference, that equation does really good prediction. I recommend using it to predict the strain. With this, I want to acknowledge the support from Center and DOT and the help of our co-author. I didn't introduce Dr. Shrinkage. He's here with us. He's one of the instrumental people doing this work initially. Thank you very much for your attention for this.